All right, so in the next and last part of this chapter on equilibrium, we're going to talk about dynamic chemical equilibrium. So dynamic implies that we're changing. That's just what the word dynamic means. So we got two definitions here that we need to understand in order to talk about these pictures up here. So with reversible reactions, these guys proceed simultaneously both in the forward direction towards products and in the reverse direction toward our reactants. We are going to, our notation for a reversible reaction is a double-headed arrow, so pointing to the left and then pointing to the right. So we got a double-headed arrow. If we have an irreversible reaction, we are just going to have one arrow from reactants to products. Chemical equilibrium. So chemical equilibrium is the rate of the forward reaction is equal to the rate of the reversible reaction. So we are both moving in the forward direction, so making products, and also going back towards the reactant side at the same rate. So both are still happening, but they're happening at the same rate. So they're not changing concentrations of either of them. So both are occurring at the same time. That is what chemical equilibrium means. Okay, these pictures up here. So this is a reversible reaction. So we are going to be combining two reactants. So it looks like we have hydrogen gas and iodine gas. So we are combining our two reactants, and they're going to be making products. So we talked about our rate of reactions in the previous video, but we're combining our reactions, we're making products, and once we have used up a certain amount of our reactants, we're going to have more products, which means that we are going to be shifting towards an equilibrium. So if we have more reactants, we're going to be making some products, but eventually we're going to get to the point where we have more products and shift over to the reactant. So we're constantly moving back and forth between these two guys. So after a certain amount of time, after a reaction has occurred and we've gotten to a stabilized point, that's where we're in equilibrium. So making reactants and forming products and going back to reactants at the same time. So that's our equilibrium. We got an example here of an ambitious crossover. So we got Narnia with C.S. Lewis and then Middle Earth with J.R.R. Tolkien. And so these guys in Narnia, for some reason, want to leave Aslan's country and go over to Middle Earth, where Gandalf is. So these guys are coming over, and there's less people in Middle Earth. But once we get to a certain point where there's too many people in Middle Earth, they'll realize how great Narnia is and go back. And at this point, we're just like traveling back and forth, depending on where you want to live, because there's maybe too many people there at that time. Or whatever, but that is one way to think about it. Just constantly moving back and forth depending on how many people are there. So maybe they're introverts and don't really want to hang out with a lot of people. So, okay, so we got homogeneous and heterogeneous equilibrium. So homogeneous equilibrium, it's a reversible reaction at equilibrium, so equal forward and reverse rate, in which all the substances are in the same state. So same state, we're talking about physical state, solid, liquid, gas. Our example here is from ozone at the top of this page. We have gas ozone, and we're producing a gas. So we're keeping in the same state, so gas, gas. Heterogeneous equilibrium is a reaction at equilibrium in which one of the substances is in a different physical state. So here we have NH4, CO2, NH2, and it's a solid. I ran out of room there. It is a reversible reaction, hence the double-headed arrow like up here. But we're going to be making gas and gas. So ammonia gas and CO2 gas from this solid. So here we have a solid and we have two gases. So these are different physical states. So that is heterogeneous equilibrium. So pure solids and liquids are not considered in equilibrium because their concentrations remain constant during a reaction. Okay, let's look at Le Chatelier's principle. Okay, So we have our definition down here. When a reversible reaction at equilibrium is disrupted by a change in concentration, so maybe we're adding more reactant or more products, that's a change in concentration of those, so how much we have. Temperature, maybe we're heating or not adding heat, or pressure. So maybe we're applying pressure to this system or whatever. So the equilibrium is going to shift to relieve the stress. So if we have more reactants, we're going to shift to the left, to the right to make more products. So here is where we're going to talk about each of these in turn. So the effect of increasing change, of a concentration change on equilibrium, So increasing the concentration of one or more reactants causes a shift to the right. So if we have more reactants we can use, we're going to shift to the right to make products. Increasing the concentration of one or more products causes the reaction to shift left. So if we have more products on this side, we have more products to use up that we can convert to reactants. So we're going to shift to the left towards our reactants. So whichever one is in higher concentration, that we're shifting the opposite way. Okay, so let's do this example. Consider the following reaction at equilibrium. So we have a solid, and a gas. So this is a heterogeneous equilibrium. A reversible reaction because of the double-headed arrow. All right, so what is the effect of adding additional CO2? So CO2 is in our products to the reaction mixture. So if we're adding more products, these guys are going to combine to relieve the stress of having more products. So we're going to shift left. So we're shifting the opposite way. We got more of these guys, so we're going to shift left to make more of that calcium carbonate solid. What is the effect of adding additional calcium carbonate? So if we have more reactants, we have more reactant that we get to use up to make our products. So we're going to shift to the right. Okay, now for volume. The effect of volume change on equilibrium. So if we are decreasing our volume, this is going to cause a reaction to shift in the direction of fewer gas molecules. So we want to relieve that pressure of the gas molecules. So gas molecules bouncing off the walls of a container, that's how we measure pressure. So we want decreasing the volume causes a shift in the fewer gas molecules. So we'll go through an example in just a second. But increasing volume causes the reaction to shift in the direction of more gas molecules. Those gas molecules have more room to move about, and they want to do that. So let's look at these ones. So we're looking at KClO3, and then potassium chloride, and then oxygen. So potassium chlorate solid, potassium chloride solid, and then oxygen gas. What is the effect of decreasing volume in the reaction mixture? So we have a gas over here. So if we are decreasing the volume, we want to produce less gas. So we are going to shift to where we don't have any gas, so solid. The gas molecules don't have very much room to move around because of the decreasing volume. So we gotta shift to where there just aren't gas molecules, really. Increasing the volume of the reaction mixture, so we have more volume, which means that our gases are going to be happy and they get to move around a lot more. So we're going to shift to the right where we're producing gases. All right, effective temperature change on equilibrium. So we're looking at two different reactions. So increasing temperature is going to shift endothermic reactions to the right. So endothermic means that we're putting in energy. Energy is being absorbed, which means we get to use up that energy to make products. Increasing temperature shifts exothermic reactions to the right. So for exothermic, we are releasing energy. So if we are increasing our temperature in our we're releasing energy in our products. We'll go through an example in just a second. We get to use up that heat in our product side, and we're going to make those reactants. Okay, so let's look at these two guys. So we have an endothermic reaction here. So if we are adding heat to an endothermic reaction, we're shifting right to make products. We have the energy to make the products. If, however, we are removing heat, we're going to be shifting to the left, so the opposite there. So adding heat, we're shifting to the right because we have enough energy to make our products. If we're removing heat, we are staying with the reactants. We have more reactants at that point because we don't have the heat to make our products. For exothermic reactions, so here, exothermic, we're releasing heat. So if we are adding heat on this side, we get that reaction to occur over here. But exothermic on this side, so if we're removing heat, we are shifting to the right because we have more heat, I guess, that we can make. Okay, so let's look at endothermic and exothermic. So 1, what is the effect of increasing the temperature of the reaction mixture? Oh, this is endothermic. So that means we're looking at this side over here. So if we're putting in heat, increasing temperature, we get to make products. So if we're increasing temperature over here, we get to make products, so we're shifting to the right. Endothermic, we need to put energy in order to make products. If we're decreasing temperature, we don't have enough energy. So we're removing heat. We don't have enough energy to get to the products, which means our reaction shifts to the left. We don't have enough energy to make products, so we have to stay with the reactants. All right. Our last page is a bunch of student exercises, so let's go through those pretty quickly. So what are the three factors that determine the overall reaction or rate of a chemical reaction? So that was on first page of your chapter handout. So collision frequency, energy of collisions, and orientation of those collisions. According to Le Chatelier's principle, what effect will increasing the temperature have on the following equilibria? So we got these three guys. So here we're exothermic, we're releasing heat energy. Exothermic for B, releasing heat energy. C is endothermic. We need to put energy in. So we're increasing the temperature. So if we're increasing the temperature in our system, we're shifting to the left. So increasing our temperature, we got the heat energy over here. We're shifting over to the left to make our reactants. Same over here. We got heat energy over here. We have more heat on our product side, so we need to move to the left to use up that heat, to fix that excess heat on our reactant side. Okay, and for endothermic, if we are increasing the temperature, we get to use up that energy, that heat energy here to form our product. So we're shifting to the right. 3, what do cold automobile batteries and food in the freezer have in common? Okay, so our reaction rates are going to decrease with decreasing temperatures. So we put food in the freezer so that our processes that make our food go bad, so like maybe bacteria in your food, we're going to slow down those bacteria so that they don't spoil your food as quickly. And then automobile batteries, even with like double, AAA batteries that you put in the freezer, we're slowing down the reaction rates that are occurring in those batteries, the chemical reactions, so that we're not just wasting those reactions. All right, 4. What would be the effect of each of the following have on this equilibrium? So we have carbon monoxide, water, CO2 gas, carbon dioxide, and then hydrogen gas. So they're all gases. So that means this is a homogeneous equilibrium, all the same state. And it is exothermic because we are releasing heat. All right. So the removal of hydrogen gas. So if we have less hydrogen gas on this side, we're going to be shifting to the right to make more. We're going to fill in that hole of losing hydrogen gas. So we have more room to make that product. A decrease in total volume. So with gases, if we're decreasing our volume, we're going to make less gas molecules. If we increase volume, we're going to shift to the side that has more gas molecules. Notice how we have the same amount of gas molecules on both sides. We could look at our coefficients out in front and also count those, but these are all ones. So we have 2 gas molecules on this side, and 2 gas molecules. Technically, these are moles. So 2 moles of gas on this side, 2 moles of gas on this side. So decreasing total volume, we're not going to have a change. We have the same number of moles. If we had more moles on one side, we would shift the other way because we want less gas if we're decreasing our total volume. All right, and the removal of heat. If we're taking away heat, we're going to shift to the right. We can't shift to the left because we won't have enough heat energy to get there. So we got to stay going to the right. Removing heat. That also is going to help us produce some heat if we're moving to the right. Okay. What effect, if any, will each of the following have on the following reaction at equilibrium? Okay, so this, here we go. We have gas, gas, and a gas. So this is a homogeneous equilibrium. We have 3 moles of gas on this side and 2 moles here. And it's exothermic because we're producing heat. All right, if we are adding CO2, we're adding a reactant, so we're going to shift towards the product. We're going to use up that reaction and shift to the other side. If we're removing oxygen, that means we're shifting to the left to produce more oxygen, to fill that hole where we took out oxygen. Cooling the reaction system, so we're going to be shifting to the right to produce heat. So if we're cooling it down, we want to produce some heat to heat it up. Increasing the pressure, so decreasing volume. If we're decreasing volume, we're going to shift to the side that has less moles of gas. So here we have 3 on reactant side and we have 2 on our product side. So we're going to shift to the right where there's less gas because our gases don't really like high pressure. What would be the effect of the following on the equilibrium involving the reaction of coal, that should say coal, not coke, carbon, coal is solid carbon, sorry, with steam to give carbon monoxide and hydrogen. So we got solid, gas, gas, gas. So we have more moles of gas on our products. So if we are adding steam, which is water vapor, we're going to shift to the right. We have more reactants to use up, so we're shifting to the right to use up that steam, the water vapor. Increase in pressure, so decrease in volume. We have more gas molecules on the right, so we're going to shift left to where we have less gas molecules. The removal of hydrogen as it is produced. So if we are removing hydrogen, we're going to shift to the right to produce more hydrogen to keep that in equilibrium. All right, charcoal reacts with steam according to the equation from above that we just talked about. So we're going to put in heat in order to make carbon monoxide and hydrogen. So this is endothermic. We got to put in heat. All right, predict the direction of equilibrium shift for each of the following. Holy cow. All right, A, we are increasing the concentration of water vapor. So if we are adding something to our reactants, we're going to use up those reactants to shift to product. If we're decreasing a reactant, we're going to shift to the left to make more of that reactant. Increasing carbon monoxide. So carbon monoxide is a product, so we need to shift to the reactant side in order to use up that product. So we're shifting to the left. Decreasing hydrogen, so hydrogen is on the product side. If we are decreasing hydrogen concentration, we're going to shift to the right to make more hydrogen gas. Increasing temperature, so we're going to shift to the right. We have more heat energy to use up. We're shifting to the right. We're going to use that heat energy to form our products. Decrease volume, so we're going to shift to the left because on the product side, on the right, we have 2 moles of gas. And on the reactant side, we only have 1 mole. So we're shifting to where we have less moles of gas because we are decreasing our volume. If we are adding a catalyst, we're going to shift to the right. That means we have to use less heat energy because the catalyst is going to decrease our activation energy. The heat energy is going to we're going to add in the heat energy to reach that threshold for activation energy. But with a catalyst, it's going to just go a lot faster. We don't need much heat, so we're shifting to the right. we're adding charcoal, which is solid carbon, we're shifting to the right. We're going to use up that charcoal on the left to make carbon monoxide and hydrogen. Okay, at this point, you can do the worksheet for chemical equilibrium. And that is the end of chapter 16.